So Skyline itself actually started as this only SRM, and for a while I would, even after we added new things, you'd say Skyline, people go, oh, that SRM tool, but it's really quite flexible and does anything that is now, chromatography-based quantification. So it's not going to do spectrum-based quantification, it's not going to do spectral counting, and it's not going to do the kind of spectrum-based counting, the isobaric tagging like TMT or iTrack. But all these other methods that we've been hearing about, this is the same schematic you just saw from Brian, so I can kind of skip over that. But I guess I do also think about these in these two very broad categories of PRM and SRM, which are targeted, meaning they're inherently targeted. You can't run these methods without thinking ahead about what you're targeting. So whereas these two methods, DIA and DDA, you can, in terms of acquisition, you can just set the mass spectrometer up with some broad parameters, and then you can basically collect data about anything. So, and then Brian's giving you some clear reasons why you might want to go targeted. You're going to get more, higher precision data in a lot of cases. And so if you can think ahead, and certainly there are a lot of clinical applications and pharma applications where people are now doing a lot more targeting. Skyline itself is, it's in its 11th year of development, and actually a lot of these numbers are behind. I think I maybe didn't update this, but it's a big project, and learning it can be a job qualification now. I definitely meet people who are like, oh, I want somebody with Skyline experience, and one of the big parts of that is that it works on all the 6 big instrument vendors. So it works on, so if you're using an Orbitrap right now and you go to another lab and they're using one of these Bruker machines, it'll work on that as well. So here it is, multiple instrument vendors. These are all the instrument vendors. About 2/3 of our funding actually comes from these instrument vendors now. Another third comes from NIH grant funding. And we work very closely with people at all these vendors to make sure that Skyline stays working with their instruments. This is the sort of up to yesterday view of this growth of Skyline. I kind of think it's slowed down some in the last several years, but it's still clearly a popular tool and again useful to know. I think from this, one thing I can say for sure is that we've utterly failed to make mass spec so interesting that people do it between Christmas and New Year's. This is a view that shows new version adoption, which I pay a lot of attention to. It's a statement robust and high quality. We keep Skyline throughout many cycles of development and releases, I feel like the reason I created this view is because if we got stuck down here at 85% or even 70%, then there are in fact this gray line is the people that are actually using. The difference between the blue and the gray is the people that are using Skyline daily. That's also expressed as this blue over here. At least that every 2 to 3 weeks is a misnomer. So a lot of people use that. About 20% of our users are using that, from our measurements. And Skyline is also worldwide, so I think some of you are not from around Boston. It's allowed me to travel all over the world. Certainly, the U.S. and Europe were very early adopters, and it's spread to places like Brazil, India, the Far East, and Australia, and actually even South Africa, where I'm going in December. There's lots of interest, and it could allow you. I know one of the original Skyline users started in New York City and is now in Brisbane, Australia, and also he's coming on a course in September. So lots of ability to move around the world doing mass spectrometry and doing, quantitative proteomics. This is zoom in on the map of the U.S. When I'm in a particular country, or when I'm in Europe, I like to sort of zoom in on the area. We're over here on the East Coast, and there's one of eventually all these maps just of where there's population. So yeah, we're here in Cambridge. That's the second most, in the past 6 months, that's where, and actually you can see that some of these places show up twice, Cambridge and Boston and San Francisco. I guess pretty early on, early on, I realized that Skyline wasn't going to be a viral product, and even with this this amazing growth, we're never going to catch up to Facebook and Instagram and those other things. And that actually it took a lot of teaching to get people to do these methods. And in fact, when I started, it was SRM, it was targeted proteomics, and I looked around and I went, wow, there's maybe 10, 20 labs actually doing this right now. And so we had a very small market, and in order to grow the number of people that could use this stuff, we had to teach it. And so starting in 2013, actually, the Aebersol lab, I'd like to thank Rudy Aebersol, has been a big proponent both of technology. He doesn't come from an informatics background, but he's funded a lot of informatics, starting with the transproteomic pipeline, for which he did a course, and then once he got into SRM and targeted quant, his group was the first group to do a course of this type in 2013. Olga Vitek and I both, and Mina, all joined that course, and then all of this other stuff has grown out of that. Last year was kind of a crazy banner year. I was certainly tired by the end of it. We had more week-long sessions than ever before, and probably about the same number of conference workshops. These were the only two sort of dedicated sessions to DIA swath, this one in Boston that we're at right now, and also a full week at ETH in Zurich. However, 2019, unfortunately, with Rudy moving toward retirement and some key people leaving his lab, ETH is not going to have the DIA swath course, and so this becomes our only fully dedicated DIA session that you're at right now. But certainly, if a number of these others have DIA material in them, and if you come to them, they're great places to learn more about Skyline and targeted proteomics. There's also, once you leave here, there's a lot of tutorials, 17 different webinars. All the webinars are built on this, what we're going to be doing here later, where I'm going to be walking you through some steps and analyzing some real data with Skyline, and you can do that with a written tutorial, or you can do that with a webinar. All of those 17 webinars come with a data set and spend some time walking you through it. Yeah, those are the webinars. So, a big principle of Skyline, I was telling Brian recently that I come from my early software days were working at Microsoft on debuggers. Well, not debuggers, on development tools, on an environment for developing software, and very much involved with a debugger. And I feel like that Skyline is a little bit of a data debugging tool and a data understanding tool. We focus a lot on how quickly you can understand your data and how you can understand your data more, because we make mistakes all the time. And so I'm going to move into a session where I'm going to show you some plots and some things that that if you didn't have the tools, you just go right by. If you can't see what's going on with the data, then you're just going to go right by it. And so no matter what kind of experiment you are doing, I would argue mass spectrometry is really hard to see, and you would like to see more. And that's what Skyline's designed to do. It's designed to help you to see more. It's designed to help you to when you ask a question, not have to spend an hour answering the question. You can ask a question, answer it. Ask your next question, answer it. And so I came up after reading Daniel Kahneman, who's a award-winning psychologist, Nobel Prize-winning psychologist, who had this Wizziati, and it's I guess what I see is all there is. So that's so it's the human mind just has a really hard time making up information that it doesn't see. And so you will come up with an explanation of the information you see, and it might be wrong if you're not seeing it. And so I changed that to what you see is what you believe. So if you see a limited set of information, then you will have an answer that is limited in some way, and if you're not seeing the whole story, you might be wrong. So a lot of tools that get produced sort of hurry you past all the grubby details of what's going on, and Brian's been showing you some of the grubby details and why they become problematic. But if you use a set of tools that give you this kind of view, which is this is a true satellite image, and you can learn something from it. So we can learn that there's a lot of center pivot irrigation going on, and we can wonder, well, certainly there's difference in expression, and we can wonder, well, what's going on with these plots? Are they intentionally left fallow, or have they died, or what's going on? And this is our satellite view in proteomics, right? And there are tools that will just like, spit that out for you, or spit out the information that you then use to do this, where you have all the samples and then all your things queried, and now you may be like, okay, I've got all my numbers, now I can start running statistics and coming up with interesting insights. But I'm going to say that, like, wow, there's a lot more that might have gone on underneath there, and if you just rush to this, then you're in danger of believing it even when you should. So the question is, what's underneath these values? So now I'm going to give you a set of things, and we're going to hopefully pause long enough for you to get oriented to what you're seeing, because I know that a lot of times we show graphs, and I find that, if I don't understand the axes, I don't really, sometimes people throw up graphs, and I'm like, whoa, I'm not really quite clear what you're showing me. So, and then we're going to try to come up with explanations for it. So this is a single peptide, and these are the isotopes of that peptide. So this is an MS1 extraction, and this is Skyline's top-down view of it. So you can see these little the cross bars are the apexes of the peak, and then you get another bar that shows you the full width at half max. And this is retention time. So you're looking down at these peaks. So what's going on with retention time? Does everybody go like, yeah, that's about how my data looks too? Or does anybody see any problems here, or what? What do you think of this? As if I'm monitoring a single peptide, is this what I expect to see in terms of retention times? Is the chromatography very good? Does anybody have an explanation? What? Difference of matrix, yeah. So come up with some ideas, explanations. So I'm denying you some information. How do you explain this? Because, like, yeah, it's true. So let's just say, in the perfect world, what do I expect? Yeah, just a straight line. It's always a good idea to ask, what am I expecting? And then what am I really seeing? And then even in a not perfect world, maybe I expect to see some like this, but I don't expect it to be jumping around all over the place like that. That's crazy. That's a lot of variance. That's what I said. I went, whoa, I'm not sure I've seen any, retention time variance. So do we think, maybe it's just picking between two things, and it's randomly jumping, and it's choosing, sometimes it's choosing one or choosing another. Anybody have any other? Okay, so I'm gonna, so what? A PTM, yeah, so there might be maybe it's a PTM, and yeah, it's what Brian showed us, and this is one phosphorylated type, and this is another phosphorylated type, right? And so we could go around and around and come up with ideas and write them all down, and I've seen people do this with statistics, where even Jared Eggertson in our old lab was like going around with these statistics, and when I do this, and I finally said, look at the chromatograms. What's going on with the chromatograms? And the whole thing turned out to be that the data had carboxymethylation, and we had our experiment set up to look for carbamide methylation on the cysteines, and that was the end. But you had to come down from the statistical level of looking at things. So this is I had to use a debugger to figure this out, and then I added this feature to Skyline. So the thing is that this is just a logical ordering, and you can see so this is a calibration curve experiment, and these are different concentrations. And they just got, when I imported them into Skyline, they just got sorted into that order. But that's not the order they were acquired in. And so if I sort by acquired time order, then all of a sudden I see this. So what's the explanation? There's just, maybe here we're in, we didn't do enough to condition the column, and so the column kind of conditions here, and then it goes along pretty well, and then so, but that's a different what we came up with, without a full visibility into this. And so Skyline now makes this very easy, and when we look at data, we'll do some, let's look at what the order they were acquired in, because frequently if it's you don't own the data, you might not know this. I didn't know it until I did. And then so that's that's a little strange, but then if we do retention time alignment, so this is with everything aligned, then now I get even better retention time stability, and that just kind of goes away. So that's something called retention time alignment. Skyline makes it easy to do, and then you can get an even better sense of, well, they actually are really acquired at very, very similar times. So so what? Oh, actually, well, anyway, what happened here? Column change, I didn't hide the dates. So I put some information in here that you wouldn't necessarily have. If I'd done this, then I could go, whoa, so yeah. And I didn't know this. I just started with this data, and I went, whoa, what happened to the retention times there? And it turns out that they were collected a month apart, and so it's probably a different column. And the way that's pretty easy to learn in Skyline 2 now, you can bring up these reports. And you can get at this acquired time. So here I showed you we sort by the acquired time, and then here you can actually get at the numeric values for the acquired time in Skyline pretty quickly. So you can ask these questions and then get answers really quickly, because Skyline makes everything very dynamic for you to look at. So that was that one. Now, in this case, this is an SRM experiment, and I align by IRT, the IRT that Brian was just explaining, and when I do that, it disappears. So that ability to align to these anchor peptides allows us to get, here we're actually showing IRT scores. So Brian was showing that with a score of 60, and now here's this thing with a score of 40. The IRT scores for the peptides stay stable because of that alignment. Okay, so, well, this is actually the same thing. So this is the same data set, again, collected a month apart, and here are two peptides from that data set. What's the red and what's the blue? It becomes important now. What? Heavy and light, yeah. So people who are here for the calibrated quantification probably are pretty well oriented to that. Skyline is generally showing blue as the heavy and red as the light. And so most of the peptides, this was maybe monitoring 150 peptides or something in this experiment. Most of the peptides that were being monitored did something like this, but I chose sort of the most extreme one. This is like a 4 to 5-fold change, just because I'm measuring some in February and some in March. And this peptide actually goes the other way. So this is I say, like, sometimes we use global normalization, like while we're here, we're going to be using maybe median normalization. We use some normalization that we apply to just everything, because in a lot of cases, similar things are happening to a lot of our analytes, and we can do that, but it's not as good as having a heavy labeled peptide where we know we've already done method development and we know that it acts similarly. So if I do the normalization where I take the ratios between the two, then all of a sudden now I can't tell anymore where exactly was the column changed. I don't know. Okay, so we're also going to be working with it. So this will be different for people. Well, actually, maybe if you did PRM, you might have actually seen this in the first thing. But Skyline also makes it really easy to get at the spectra, the underlying spectra. So these chromatograms frequently get extracted from spectra. If you're doing SRM, they just come from the triple quadrupole and there's no spectra involved. But if you're doing PRM, DIA, or DDA, then you might be looking at this peak and going, okay, I want to see the spectrum that point was extracted from, and here it is, right? So here's the isotopic distribution of the ion, and we see the single carbon-13 and then double carbon-13, and we see this very classic pattern. Okay, so can anybody tell me what this is? So I'm denying you the information of what it is. What do you, any hypotheses? Any hypotheses what this is? Is that an interference? Is that this, a tail? Is that the instrument hasn't been calibrated? Why would that be?
Sometimes like there's a shift and there's some column is not kind of contaminated.
Okay, so that would be, a sort of second elution of either tailing of my peptide or a second elution of my peptide. I'll frequently look up here and go, is there a proline in there? I've been told that like proline peptides sometimes have a double elution, right? But it's hard to answer that question unless I can just click on it, and that's what I can do in Skyline. And now I can look at it. Now, what's the explanation? It's clear. Yeah, maybe it's a deamination, or like does a deamination? It will actually shift it this way too. Because the other thing is it's not as well. Whoops. It's not as well. So there's something. Whoa. There's something here that is lighter. So this would be the deaminated peak, because this is heavier, right? And then this thing that comes afterward is lighter by almost one. It's a little bit more than 1 MZ lighter. Actually, since it's doubly charged, right? It's doubly charged. It's 2 MZ change. That's what no, it's 1, sorry, because that's a half. Okay, so anyway, but it's not as well centered. If we actually use Skyline to integrate this peak, it would tell us that this is not, so this is very close to 2 ppm to what we're expecting. This is going to be more like, 10 ppm or something. It'll be minus, this is plus 2 ppm. So it's a little bit shifted too far to the right, and then this is going to be like minus 10 ppm. And then when we first implemented this in Skyline, Jared Eggerson again in the lab said, wow, it's like pulling the blinders off, because to get that information before we did that, you had to actually go and bring up Excalibur and get to the spectrum, and but now it's there. So yeah, so we've been looking at data that these are actually from DIA runs. We've been looking at a number of things that are from DIA runs. This is how Skyline presents information from DIA runs, where you're looking at the precursor isotopes extracted from MS1. So what can people tell me about this experiment? Any new, this is the same experiment, it's got this weird, like thing that happened to the chromatography. These are where the MS spectra were acquired, it's DIA spectra. So these were actually acquired here and here. Why do they get acquired on either side? Why don't I have just, wouldn't I like just one right in the middle? Yeah, dynamic exclusion, and so this got acquired here, and then it got dynamically excluded for a while, and then it got acquired again. And sort of ironically, the faster the instrument, the more likely this is to be way down here. And then it will be dynamically excluded. So, but you do see this, skipping of the apex of the peak. Okay, so what over here? What kind of experiment was it? Yeah, it's a dilution series, and this is the acquired order. We know that because when it's not the acquired order, we have a whole lot of jumping around in the retention time, and so we acquired them in 3 cycles rather than 1, 2, 3, 1, 2, 3. So you can learn a lot just by looking at these plots, right? A screen full of Skyline information can show you quite a lot about your experiments. Yeah.
When I load into Skyline files that contain MS information, I get all these IDs shown, and also I get the sequence displayed above of my spectrum. However, there is no database search or something happened yet. So how does Skyline decide that this amino acid sequence based on that spectral information?
There's no database search?
No, not yet. I just load in the raw data, and Skyline will show me this MS spectrum and the amino acid sequence above it. So it matches the target list to the fragment ions. But how does it?
Are you using MIDAS?
Yes.
Yeah, so that's a special MIDAS feature. So yeah, I knew, because he had told me that he was using multi-sample WIF files, and so SciAx has this thing called MIDAS, which is basically a triggered MS based on SRM. And so Skyline, when you load in that data, Skyline will pull the triggered spectra out and then associate them with the peptide. So it's a special thing that we're not going to deal with here. But yeah, so that's MIDAS for SciAx. Okay, so now by the end of this course, we're really going to be focused on statistical differences. Right? And is something statistically significant? So if I for a moment just blind you to the colors and the extra information that's on this plot, who thinks that the difference between sample 1 and 2 and sample 3 and 2 is statistically significant? So, only one person. Yeah? So why wouldn't it be statistically significant? Well, I'm just saying, like, the levels of these things. So based on the variance you see in the 3 acquisitions, actually, I really need to go figure out what the p-value or the q-value is for this. But who can tell me, who can guess a p-value for a t-test between this set and this set? I gotta really do these t-tests so I can tell you. It's probably like 0.00001, like it's like certainly way below 0.5. So statistically, if you put these data into MS Stats, it will go, Eureka! This thing is a major change. Okay, but so now unblinded for a moment, Skyline's giving you a whole bunch of information. What might be wrong with these data? Yeah, like what the, I.P is 0.55, that's not very good, you know, and down here it's 0.9, and so we already have a clue that, yeah, maybe let's go look at the chromatograms and see what's going on. Okay, so here we get, so this is the information that Skyline gives us. This is again extracting from MS1. So the blue is the monoisotopic, the purple is the +1, and the brown is the +2, right? And so we see that there's an ID. So our mass spectrometer has isolated an MS that got ID'd as our peptide in every sample 1, right? Every replicate of sample 1, I've got an ID. How about sample 3? Well, I missed one, but how do you feel about this one? These light blue lines are more information Skyline's giving you. It's doing retention time alignment, and it's saying like, well, if there were an ID in here, we'd expect it to be right about there. That's where we're seeing the IDs in the other one. So, you know, I feel pretty good about that. That's, again, if we went back to this plot, that thing has that's sample 3A, that thing has a 0.96 I.P, right? And then we can even look at, you know, -2 ppm, -4 ppm, -3 ppm, -2, 4, 2. So pretty, 3. Pretty consistent, but what's going on here? That's like, you know, -10 ppm, and it's actually shifted a little bit to the right. But who thinks that there's some other tool that could actually extract the right peak area for this? Because that's where it's supposed to be. Maybe this little blip is it. You know, that's actually kind of you know, or maybe that little blip is it. So there's potentially some chromatographic separation between what's getting picked by Skyline, but it would be really hard to get. And that's one of the things that DIA will give us is the ability to use fragment ions to separate these two different precursors. That like there's no tool, you know, MaxQuant's not going to do it. None of these tools are going to be able to give you a really good peak area for this peptide in this case. Okay, so here's another one. Who thinks that these are statistically significant? There's a statistically significant difference. Got one person. Okay, come on, like really, this is even more extreme. This is like a point, you know.
10 to the 9, -9.
This is 1 to the -9, right? So yeah, wow. Any statistical tool is going to go. That is so interesting. This is a biomarker for sure. And then does anybody see any information that makes you doubt? Like, you know, I don't want to put this into MS Stats because 0.96 isn't quite as good as 0.97? Probably not. Okay. What? Yeah, who knows? Let's go. So again, can't tell. And if we just go straight to the satellite view and then pump it through MS Stats, we're going to get, yes, this is totally interesting. And one of the nice things is after MS Stats tells you it's totally interesting, that's how I found this, is I used this statistical tool and it said, wow, that's totally interesting. And then I went and looked at all the totally interesting things, and some of them had these problems. So you can do this after the fact too. So in this case, so here we go, okay, again, it gets ID'd in every run, right? And but what I like to talk about is something called the chromatographic landscape. So when you don't have just perfectly one peak, frequently you can learn something from the other peaks you see. And so in this case, there's 2 peaks, and we pick the one to the right, and there's an ID in it. And this one is minus 2 ppm, and this one's plus 20 ppm. This one's minus 3, this one's plus 20, this one's plus 20, this one's minus 3. So their mass errors are really consistent. They're very consistent in retention time. You know, down here, this one's a little bit bigger, and this one's kind of more looking like a shoulder, and it's plus 10 ppm instead of plus 20. But this stays plus 3, plus 5-ish. And then up here, well, my ID is a little bit to the right, and, you know, wow, this is 20 ppm off. So in fact, if you use centroiding and a narrower window, we could get rid of this peak entirely. In our modern processing, we probably would, but this is an older processing. But now, you know, there are going to be other cases where you can't. But if you zoom in closely, you can see, wow, this other peak is still there. And here, like, there's no tool that's going to think that this is not just a shoulder. Right? It's not going to, you know, and there's way too much interference to actually get a real peak area here. So, but the fact that you can look at it and figure this out gives you a chance to go, okay, right, I'm not going to go order this synthetic, you know, I'm not going to go order a synthetic peptide for this, because you can see this is 20 million, this is 20 million, so it's really staying pretty consistent all the way through, not a biomarker, it's just a false discovery. Okay, yeah, I'm going to skip this. Okay, so here's another case where we had just implemented mProphet. Dario Amade did it from the Malik lab at Stanford, and we implemented basically the open, you know, what Hannes Rost from the Aebersold lab had implemented as open swath. But we knew that we were missing some scores, and we were missing this Y series score, isotope correlation, isotope overlap. And those scores were not easy for us to reproduce. You know, Hannes's tool did it, but it was not easy for Skyline. So I was like, let's just do it without it, and we'll see how big an impact it has. So here was the Skyline default at the time. This was Skyline with mProphet was this. And this was Skyline sort of corrected with our best attempt to come up with a static set of scores at the time. And then this is what we saw with open swath, was this purple. So what's, you know, who can come up with an explanation for that? What do you think? Were we done? Did we need to keep, you know, do we need to keep working? Obviously, we need to keep working, but here's another piece of information. This is open swath, limited to only, you know, we dropped the other scores. So it's open swath had 10 scores, and we dropped the 3 scores that we hadn't implemented, and it didn't come down to here. So we're still going like, what? You know, why? We seem to have a lot of work to do to close this gap, but there's not anywhere near that big a gap if we limit it to the same scores that we've implemented. So it turned out that there was just an incompatibility between that we had a new SciAx WIF reader that sort of changed the centers of all the windows. So we were actually extracting from DIA, and we were about a third of the time we were extracting from the wrong window. And that was actually not that hard to figure out once we used Skyline, because we could go and say, wow, you know, open swath is picking a peak at a place where there's no peak at all. Like, it's not like we're doing a bad job scoring, we just don't see anything to pick. And then eventually we were able to figure that out. So again, visibility was key, and as soon as we did that, it turned out, well, there was no other work to be done, and Skyline you know, actually did very, Skyline with mProphet was green and it ended up higher and did very similar to open swath. Okay, yeah, so So here's another. This was another case. This is this is a paper comparing all these tools for DIA use, and this was the very first set of statistics that the author came out with, and it said that wow, Skyline found 27,000 peptides, and Spectronaut and OpenSwath found 41, 42-ish. You know, and then there were people who really wanted to publish this. But we were like, wait a second, you know, we've done these other tests and we haven't seen anything like that. So we went and did some more investigation, and who has an explanation for why these are so different? I mean, what's the obvious explanation? The common explanation of a number of people on the telephone when we had the call about these statistics. The Skyline's just not as good. You know, these other things, you know, just do better. But it actually took us probably a year after that phone call to publish maybe even more, to publish the paper, because we just kept, you know, we came up with new things about DIA-Umpire. We just kept coming up with new things that we hadn't realized because we kept looking deeper. So it's very dangerous to just go out with your first, like, oh, I ran statistics and it says this. So in this case, again, I used looking at chromatograms, and happily both Spectronaut and Skyline make it pretty easy to look at chromatograms. So I looked at how Skyline was. I just took something where Skyline and Spectronaut like had wildly different opinions of how good the peak was. And Skyline was picking this, and Spectronaut was picking this, which is pretty good, but clearly Skyline's just not really picking that up because of the interference next to it. And I was like, oh, why is this so much dirtier than this? And that turned out to be just a misunderstanding between the person who ran the data and me. He said, so 10,000 resolving power, and I thought, well, he'd collect the data. Turned out he hadn't collected the data, but he was asking me, do I just use 10,000 resolving power, which was the Skyline default at the time? And I was like, yeah, sure. You know, okay, if that's what you used. And it turned out it was way too wide. I should have looked at the data earlier. And then this is about the resolving power that we would have just suggested. So right off the bat, what we knew, we were saying, you know, Mike and I really believe that in this profile mode data, you wanted to sort of extract all the ions that you could. And so we would have said 30,000 resolving power got us that. And then once I did a really thorough analysis after this, and what we found was that actually 60,000 resolving power was the best, and that even actually 10 ppm resolving power, if you did pre-centroiding with the centroiding algorithm provided by SciEx, and then used 10 ppm centroided, you did even better, because as we saw, there are these things that centroided, they're going to be, you know, too far out of your range to be considered, so you get even better chromatogram extraction. But we thought that might mess up the quantification. So this is how you set that in Skyline. We'll be playing with that later. There's also something called SkylineRunner, or Skyline has a command line that you can, and we'll look at that too. So you don't always have to use the Skyline UI, and especially for DIA, it's frequently, you know, better not to use the Skyline UI. And so I created all these extra things so that I could run statistics. And so this is varying resolving power with everything else held completely the same. This was the original resolving power. And then if I varied it, I found that, yeah, that's how I found that 30,000 was pretty good, 60,000 was about what we wanted. And that's the number of proteins and peptides. And so then the question of the time window, we talked about plus or minus 5 or 10, or I did an analysis of that, and that was pretty interesting too, because I was expecting that to sort of go up and then come down as I got really wide time windows, but it doesn't. it actually levels off and then continues to go up. And that's because we use a dynamic model. And what happens is as the window gets wider, retention time becomes a stronger and stronger score, because all the random things start moving away from the true retention time. There's more random space for retention time to impact. So this isn't just adding false discoveries. It actually ended up, out to 10 or 20 time window. Well, so a time window of 10 is the default, but out to 20 certainly, and even out to 30 was totally not a bad thing. So in the end, Skyline ended up with just totally comparable number to Spectronaut and OpenSWAth, and the other tools had a little bit less. So yeah, and then we were like, well, so DIA-Umpire was coming up with totally different things. Because DIA-Umpire is a different method. It will search the entire FAST A. It generates spectra. It works like that MS to the E thing that Brian was talking about. We're like, well, what? We needed to validate these 7,000 peptides, non-modified human peptides that DIA-Umpire was identifying that weren't in the library. So all these other tools are going from the library, and these weren't in the library. And so they're only identified by DIA-Umpire. And then if I used the DIA-Umpire information, then Skyline identified them really confidently, but then people said, well, you're just saying you can find the same things as DIA-Umpire, but what if they're not really the right things? So Biognosis contributed an assay library that actually had spectra and retention times for these things, and then we had everybody perform the new search coordinates. And this is what that ended up looking like. So really, at this point, there are not very many of those things that are uniquely found by only one tool. But this was kind of strange for OpenSWAth. I had really gotten to the point where I felt like, okay, OpenSWAth, Spectronaut, and Skyline all are performing very similarly. And so we look here, and wow, OpenSWAth is missing like 2,000 things. Anybody have an explanation for that? Well, you have to, there's the obvious explanation, well, it's just not as good. But I had already been looking at the data with, as I said, Skyline is a ±5 minute retention time window. And so these are actually residuals. So this is how far we find a peptide from where we expect to find it, right? And this is with ±5. This is a 10-minute window, ±5. So does anybody see anything that's makes you go, huh? Well, this kind of seems to be going like this, right? And then there, yeah. It kind of looks like it's cut off, right? So you definitely, to me, I go, okay, I wanna go back to 30 minutes or something to just see, because I've already proved to myself here that 30 minutes works just fine. So let me just open up the window a little bit and see what else is out there. And this is just a normal plot in Skyline. Skyline gives you immediate access to this plot. And so then when I open it, I guess I did open it up to 30 minutes because you can see that there's stuff 15. And what I ended up deciding was, well, 20 minutes is, you probably want to be at least 20 minutes. I don't know how much I really believe these things, right? So yeah, so when I already knew this. When I saw this, I said, hey, did you OpenSWAth guys use a 10-minute window or a 20-minute window? And they went, oops, and they reran their numbers, and now we were down to just a couple hundred things. Yeah, really easy to make these kinds of mistakes. And having tools that'll give you a lot of different visualizations. You're going to see a lot of visualizations here when we start working with Skyline. So you can, what I've been showing you, you can get access to yourself. This work led to a lot of performance improvements, one of which is that now Skyline can very easily import a lot of files in parallel, and that has, I'm gonna show you a little bit of that tomorrow afternoon. You can, we're actually gonna look at this 24 core machine where we can get to like 8 times faster than, or at least 5 times faster than doing everything one file at a time. Over time. Okay, so let's see. These are just more things where, and frequently when we're finding problems with data, this is some Bruker data that they gave us, which turned out, they said, wow, Skyline doesn't find as many things as Spectronaut in one case, and it was that the data were really poorly calibrated. And so I used R to generate these plots, but eventually worked them into Skyline. This is just a Skyline plot. Again, you can watch all about this in webinar 15, and that's now the Skyline plot showing this really weird curve-shaped mass to charge ratio. And this is the mass error. We would expect everything to be on 0, but when it's 20 ppm away at the beginning, you're going to lose a lot of stuff. And then Bruker just went, whoops, we're going to recalibrate the run, and they had a tool that they could run, and that's what came out. And so it's now just maybe 2 to 4 ppm on. Here's more IRT data. This is Skyline generate. This is an mProphet. This is an mProphet model generated. You can see that you get weights for all the scores, and you're going to generate something like this tomorrow. And this is, you can see this is thousands of peaks. This is 30,000 peaks just in this bar. So we're gonna play with some. So these are new multi-peptide plots. We're going to look at them. This was a case where we had run all kinds of statistics and I hadn't noticed that one of the runs was corrupted until looking at it in here, and all of a sudden it's like, whoa, why are the IRTs? There are no IRTs. They're getting picked completely weird. This is the Skyline team right now. Many of whom are in Seattle, still working on new features.